Hey everyone, so in this video we are going to talk a little bit about density concepts and how we can use particle diagrams to help us better understand what density is as well as the variables that are associated with it. So I have four boxes here, box A, B, C, and D. And down below I wrote what it is in the picture that would have to change in order to see a change in that variable. For example, the first one here is a change in density. If I want to see a change in density, then I need to see a change in the distance between the particles. For example, if I'm looking at picture A, I can see that there's these blue dots. Those blue particles are some distance apart. And then if I move to box B, well, those same particles, the same quantity of particles, are now closer together. And so because of that, I can say that the density of box A is certainly less than the density of box B. And that's again because the distance between them changed. We packed in B more stuff into a smaller area. So we increased the amount of stuff per unit volume, therefore we increase the density. Now, changing the mass could be changing the number of particles, or it could also be changing the size of the particles. So if I look at A compared to B, I'm going to say that the mass of each is equal to one another. So the mass of A equals the mass of B. And that's because they are both the same size. And there's 1, 2, 3, 4, 5, 6, 7, 8 in here, and then 2, 4, 6, 8 over here. So because we have the same number of particles, their masses should be equivalent. Then looking at C and D, now if you were given a question like this, you would need some more information. So let's say that the question told us that the C particles are, oh gosh, I forgot a letter. C particles are 3 times the mass of D particles. So 1 C is equivalent to 3 Ds, okay? So looking at the mass, sure, these C particles are much bigger compared to the D particles, but for every 1, 2, 3 Ds, I'm going to have 1 C, and then 1, 2, 3 for 1. So according to the relationship, from size to size, well then C's mass should be equal to D's mass. And you can also go back to density and say, all right, well, if the mass is the same and the sizes of the boxes are the same, then what else is the same? Hopefully you're saying the density. And the density is going to be the same for both of those as well. You can see, the distance between them. Sure, these are bigger, but the distance between looks pretty gosh darn equivalent. Of course, my excellent drawings may put it off a little bit. All right, and then the volume, a lot of people confuse mass with volume, especially when we're talking about the substance versus the container versus blah, blah, blah. And so we want to make sure that to have this common language that anytime we have a change in volume, it means that we're changing the size of the box or the container. And so you can see that clearly boxes A and B are equal in volume, but box B is certainly bigger than box C or box D. Just a couple of examples there. So this is how it gets broken down, and we can manipulate these variables to show then in a drawing what it would look like. So let's just say, for example, substance A. I'm going to tell you that it's a gas, okay? And we took this gas and, oh geez, that's not what I wanted. We took this gas and we squished the box. We changed the volume. We decreased that volume. So let me get my big old fat thing here. And then, okay, so now this is the volume of our box. So this is A2. A2, there we go. And I want to know what happens to the density. Okay, so in your head, I want you to picture this. We have this box A with these 8 blue particles, and now I've squished the box. What would you say is going to happen to the density? In order to answer that, let's also ask the question, what's going to happen to the distance between the particles? Well, hopefully you're going to say the distance is going to decrease because now they're going to be all squished together in this little tiny box, right? And if they are closer together, then their densities, 2, 3, 4, 5, 6, 7, oh gosh, 8. There we go. Got all 8 in there. So now the density of A2 is going to be much higher than A. There's a lot more space in box A than there is in A2. And now we can say, comparing A to B, that perhaps those are the same density, even though each box has a separate volume. You know, B is much bigger volume than A is. And so the particle diagrams just really make the formula itself, this D equals M over V, more of a visual understanding. Because if I did the same example here with A2, I would ask myself, okay, well, if the volume went down, mass stayed the same, what should density do? And I know that if I decrease the denominator, that's going to increase my density, right? But not everybody can think like that. That's a lot of in your head kind of thinking, and that's not always fun. So I really like that the particle diagrams can see the variables, and we can actually use examples to help us better understand the relationship between all three of those: density, mass, and volume. So hopefully now you guys have a better understanding of particle diagrams as well as the concepts of density being the amount of mass or stuff in a given amount of space or volume.